Well, now it's good.
Okay. Okay, so we're just kind of quickly explain kind of the rules for this presentation and seminar today. So all the microphones are going to be muted until the end of the Dr. DuBois' presentation. And any questions, please feel free to put them in the chat. And if you feel like you are comfortable asking the question, then you guys can go ahead and ask it after the presentation. If not, you can ask one of us moderators to try to ask it for you. And just remember to please be respectful and courteous, and this is a safe space for everybody. And yeah, let's try to have fun and really just kind of learn. Okay, so now let's get to the good stuff. So today we're going to be hosting Dr. Amy DuBois, and she will be speaking about her career and experience. Dr. DuBois' career has taken her places across the U.S. from Alabama to Wisconsin to California, and now in Washington, D.C. at the U.S. Navy Research Lab. She has shown nothing but success in a field widely dominated by men. Her drive and charisma has taken her to work on one of the most important problems in our lifetime, nuclear fusion. Setting up this event, we hope that Dr. DuBois' journey will inspire and motivate and shed light on a career that often goes unnoticed. All right, so please welcome Dr. DuBois, and she's going to start her presentation now.
All right. Thank you, Ernesto and Astrid and Carlton. I'm glad to be here to be able to share my experience and everything with everybody. So I'm going to be talking about what it's like to pursue a career in physics today. As Ernesto said, I now work at the U.S. Naval Research Lab in the Plasma Physics Division here in Washington, D.C. I just started working there not quite a year ago, moved to Virginia last July. So we'll go ahead and get started. So I guess my journey starts, I originally wanted to be a marine biologist. I wanted to play with dolphins all day, or so I thought. My senior year of high school, I took an anatomy and physiology bio 2 class, and I absolutely hated it. So I kind of had to go back and think of, well, what did I really want to be when I grow up? So going back to my childhood, I was always interested in space and astronomy. You know, here's little Amy when I was like 6 or 7. I made a poster for the elementary school science fair of the solar system. Obviously not to scale, but you know, that was kind of an interest from very young. I also did part of my growing up in Huntsville, Alabama, which is known as the Rocket City, because NASA Marshall Space Flight Center is there. And so that's kind of where our space age began. All of these engineers were working there, working on rocket engines. And so when I lived there, I had NASA engineers as neighbors on both sides. On one side of us, we had a neighbor that worked on the Hubble Space Telescope. And on the other side, we had an engineer working on the space station. And so I was really always interested in NASA. There's a great museum there in Huntsville that I used to go to all the time. And then in high school, the year before I took Bio 2, I took physics. And I thought it was really interesting. It was a lot more interesting than biology was. It was more than just memorization. It was, you know, figuring out how the world worked, all the equations and how everything worked. So my senior year of high school, I changed my mind and I decided I wanted to be a physicist at NASA. So, you know, there were a couple of questions like, what does it take to become a physicist? Will I even like being a physicist? Other than that high school class, I had no exposure to physics whatsoever. And then, you know, if I can't be a physicist at NASA right away, what other job options might there be for somebody that goes to school in physics. So those are some of the questions that I'll try to answer during this talk. So for undergrad, wanting to be a marine biologist at first, a school called Florida Tech was already kind of on my radar. They're on the east coast of Florida, a little more than halfway down. And they were known for a marine biology program, but they're actually a school that was founded by NASA engineers in 1958 because they wanted to learn more about aerospace engineering and rockets. And so they have really close ties with NASA still. So I chose Florida Tech because it was a STEM school. So I would really get to focus on physics and science, and also had a small student body, which, I wasn't looking to go to a huge state school with more people than I would ever be able to meet. And then at the time I was living in New Hampshire, which is very cold and isn't really a beach. So I was looking to move somewhere a little bit warmer, somewhere near the beach, because I like laying on the beach more than I like shoveling snow. So those were kind of the three things that I was looking for in a school. So once I got there, as I said, it's a STEM school. So, you have to take your basic humanities classes and everything, but most of my classes were in physics and science, which I really liked. And some of the classes that I found helpful were a lot of elective courses in like space science or earth science. I had to take all of the general physics classes, but classes like geophysics or planetary physics or astrophysics I thought were really interesting. Another class, scientific and technical communications, I still find helpful to this day because that class really taught me how to make scientific presentations and write technical documents or scientific papers. So I thought that was a great class to have to take as an undergrad. It felt like it gave me a head start in some of that stuff. There's undergraduate research opportunities. If you can get some opportunities like that, that's really helpful. And I'll actually talk a little bit about those on the next slide. And then programming, I was required to take C++. And so I took that, which I haven't really used a lot of C++, but it's a good course to build on because Python and IDL are used in physics and space physics a lot. Some other things to consider if you're in high school and you're looking to choose a school to go to. Some schools are considered like suitcase schools. A lot of local students will go there and then on the weekends they go home. And so I have a lot of friends who went to a school and everybody left on the weekends, but they couldn't because they were from out of state. So it made them really unhappy. Florida Tech was a very international school. So pretty much everybody stayed on the weekends, which made it a lot more fun. You had more people around to go hang out with, go to the beach, to study with, go on road trips with, stuff like that. Also, I'd recommend, talking to current students or recent graduates about the school, about the classes, about what it's like, the environment, the professors. Usually you can reach out to recruitment or even the Alumni Association to see if there's anybody who would be willing to talk with you about things like that. And then the last one I think is so important. When I applied to school, I didn't really realize how much money going to college would cost. So if you can apply for scholarships because student loans are really no joke. So for undergraduate research opportunities, they're so important for a lot of reasons. It gets you out there, you get to do really cool stuff, you get your hands on different research projects that may not be there at your institution. It shows graduate schools that you're capable of doing some research and that you want to do research. But it also opens doors. You meet a lot of people that can write you recommendations or hire you later on. So I didn't go crazy with my undergrad research opportunities. I only did a couple. The first one was on electrostatic properties of simulant Martian regolith, which is basically fake Mars dust. And so that that started out as a project at Florida Tech, but the professor I worked for also had a lab up at NASA at Kennedy Space Center. And so there was a couple of us that were working in the lab, and he invited us to do a summer internship at NASA. And so I worked a lot that summer. You can see here I am working. We would put these little solar arrays in this box right here, and then blow a bunch of the fake Mars dust on it. And then it had electrodes on it, and so you could test to see how efficient the electrodes were at scattering this dust. Now this is important for, like the rovers on Mars, because they're powered by the solar rays. And so if those get covered in dust, they die, they don't work anymore. So they were trying to come up with a way to kind of scatter that dust off of the solar panels to keep them being efficient. But, I worked a lot, but that was also the summer that the space shuttle came back online after the Columbia disaster. And so I get to see the first shuttle launch that there had been in 3 years, which was super exciting. I was about 7 miles away here. This was Space Shuttle Discovery. I actually got to see every process of the space shuttle while I worked there. From a launch, I got to see a landing up close and personal. I got to see, this is the space shuttle rolling over from when they do all the maintenance after it lands, and it was going over to the vehicle assembly building, that really tall building that they, connect the solid rocket boosters and the big orange tank to. And then I also got to see it roll out from the VAB out to the launch pad. So it was a really exciting summer for, somebody who wanted to be a physicist at NASA. I got to do that before I even graduated college. So that was really exciting for me. I also worked on an undergraduate project on the characterization of substorm latitude expansion. And so this was a project that I started my senior year of college. And this actually led to a talk and a poster presentation at a couple conferences, which was really nice. I got that experience of going and using that class, that scientific and technical communications, everything I learned in there, I got to go and present and stand at a poster. And so that becomes really important at grad school because you have to do that a lot. And then because of this research, I went to grad school at Auburn University, but before I even started, they actually sent me to a 2-week space weather summer school up in Boston. That was before I started school. So I had that experience of going in between school and learning more about space weather, because that's what I thought I wanted to do. So again, I went to Auburn University for grad school. I was there for 6.5 years. It was difficult and exciting. The first 3 years, I think, were the most difficult for me. One of the reasons was because we had 12 incoming students my first year, and I was the only girl. So that can make things overly difficult. Just being the only girl is a little terrifying once everybody starts to warm up to each other. Once we all became friends, we were all really close. All those guys, they're like my brothers. Also, you're coming from college, you're going to class, you're doing your homework. You're going to class, you're doing your homework. You're having fun on the weekends, hanging out with all your friends. But grad school, I found that was completely different. On top of juggling your classes and your homework, I was also a teaching assistant. So I was doing between 2 and 4 labs every semester. I had to grade all of the lab reports, all of the tests, and then I had to do my own office hours. And so, juggling all that work, it's difficult. I think it's difficult for everybody. And then at Auburn, qualifying exams, you take your classes your first 2 years, and then you do your qualifying exams your third year. And that was a lot of preparation, months of preparation for qualifying exams. So I think that was probably the hardest step in grad school, just forcing myself to sit there and prepare for those exams. But one of the classes that I found most helpful for my main core classes, you know, quantum and E&M and stuff, and, you know, when I got to qualifying exams, was this mathematical physics or mathematical methods class. Basically, this class takes all of the math that you learned in college, you know, your boundary value problems, your differential equations, all your calculus classes. It takes that and teaches you how to use all of that math in your physics classes. So I found that was probably the most helpful class I've ever taken. So, you know, once you finish your qualifying exams, you transition into more of a research role instead of taking classes and teaching. So this was the most fun part of grad school for me, doing the research. I worked in a small lab group. It had a couple different experiments. It was like some small experimental space plasma stuff, and then the other side of the lab was like dusty plasma stuff. So I worked on the small machine that did experimental space plasma research. And I was the only one working on the machine for the majority of my tenure in the lab. So it was awesome, and it was frustrating because I was the only one. So I did all the maintenance, I did all the electrical, all the plumbing, all the vacuum work, all the design and machining and programming. So it was a lot to do, but you learned so much by working on every aspect of a machine. And so, you know, by learning all that, you can go into any lab and start working with things because you understand how not just the experiment works, but not just the meat of the experiment, but everything that goes into the experiment. The other thing I liked about transitioning more to research was I get to go to a lot of conferences all over the world. I get to visit new cities in the US, and then my first trip out of the country was to Whistler, Canada, which is just north of Vancouver. And it was so much fun. It's a mountain town. The Winter Olympics were held there years ago. So that was a lot of fun. And also Germany and Sweden. I thought Europe was great. And of course, I collaborated with the Naval Research Lab as a grad student on my thesis project, and now I get to work there. So that's awesome that relationship kind of turned into a career for me. So my thesis project was on the laboratory investigation of dynamics of shear flows in a plasma boundary layer. So this kind of came from in the 1970s. Satellite measurements would show this broadband noise on instruments while crossing through boundary layers in the magnetosphere. And it wasn't really understood. People said, oh, it was like an instrumentation thing, or we're not really sure what it was. And so in the 80s, one of the theorists at NRL said that as these boundary layers in space get compressed by solar storms, you get these different shear-driven plasma waves that get excited depending on what the layer thickness is compared to the ion orbit, the ion dry radius. And so we did an experiment to test this. And so this was the experiment that I worked on. It's called Alexis. It's the Auburn Linear Experiment for Instability Studies. And so all of these brown things, these are the electromagnets. And then the plasma is made in this little tube. It's 2 meters long and like 10 centimeters in diameter. And all this stuff sticking off these are different kind of probes. And this was translation stage for laser and another spectrometer diagnostic there. So we basically took what measurements in space we're seeing, and we wanted to recreate that in this little experiment. So what we did to make a boundary layer, space plasma boundary layer, we have one plasma source over here on the right. This was our bigger RF source. And then we added a smaller filament plasma source over here on the end. And so this is a picture of the inside. This is a steady state experiment. So you turn on the plasmas and they're just on. It's, you don't take a shot every 7 minutes or anything. So this picture was taken from this window right here. And this is our blocking disk. And the big plasma source is on the right and the small one is on the left. And so this blocking disk basically makes a hole in the big plasma source, and then our smaller plasma source fills it in. And so this is our boundary layer right here. You can tune the plasmas so that they have different densities, so you get a density gradient across. You can also set them to different potentials so that you get a radial electric field between them. And so this was kind of how we made our boundary layer. Now, the theory said these boundary layers get compressed by these solar storms. Well, it's kind of hard to make different thickness boundary layers, but since it's actually the ratio of the thickness layer compared to the ion orbit, so it's a lot easier to change the ion orbit size by using the magnetic field than it is to change the thickness of the boundary layer. So that's what we did. Instead of changing the thickness, we just changed the ion orbit by changing the magnetic field. And so what we got was, here's the ratio of the ion orbit to the basically the boundary layer thickness. And as that ratio increases, you get these different frequency waves that are caused by the E cross B shear that pop up. And so we saw 3 different regimes, one for when this thickness was bigger than the ion dry radius, one when they were about the same, and then another regime where the ion dry radius was larger than the thickness of the boundary layer. And so basically what this is saying is this phenomena that they saw on the satellites is broadband noise. These boundary layers in space get compressed a lot faster than we did in the laboratory. We had to step through magnetic field settings. And so as this compression happens faster, all of these frequencies, you'll see them much faster than you do in the lab. And so this is what the broadband noise could have been caused by, these different shear-driven waves that are excited by this boundary layer getting smaller. So that was my thesis project. So just some advice for research-bound grad students, just to make your research life a little bit easier. I think one of the most important things in research and grad school is you have to pick an advisor that you really get along with. You two you work close, you have to work well together. You want someone that's approachable, that's going to be present in the lab, someone that's off traveling for 10 months out of the year. If they're not there, how are they going to help you? So my advisor was there a lot. He traveled a lot, but when he was in the lab, he was there. He was ready to help us. Also, are they established in the community? This could help later when you're looking for jobs. If you're looking for a job, people ask who your advisor was, and oh yeah, I know that person. And so that relationship can help you in other parts. Also, do they have the funding to pay you as a research assistant? If you have to TA throughout your research, that's going to take time away from doing research, and that could delay your graduation. So if you are going to be a TA, you have to make sure that you're going to be okay with that throughout all of your research time. And then, I wasn't really sure what I wanted to do. So I found it was good to spend time hanging around different labs, attend different group meetings to see if you're interested in that research, how the group interacts, does everybody get along, stuff like that. So, if if a professor is willing to let you join in on stuff like that, I would totally do that. And then when it comes to writing a dissertation and defending it, I think the two single most important things that I learned while I was writing and working on my presentation was definitely start writing early. It's not that difficult to, have a couple chapters done before you're done with your data analysis and stuff. I had 2 chapters. I had my hardware section and my theory section written before I even had all of my data. And then I can't stress this enough, back everything up every single day in multiple locations. I have 2 friends that while they were writing their dissertations, their hard drive crashed and they lost everything. One of them didn't back anything up anywhere, and he wasn't that far into the writing, but he was far enough that he really didn't want to start over. So definitely back everything up everywhere if you can. Some other things that may help, obviously being organized and documenting everything, that's really important. Having a good lab notebook. I color coded mine. I used to print out graphs and tape them in there. That helped later on because you think, oh, I'll just remember those settings that I used on Tuesday, and then 2 months later you're like, I don't remember what those settings were. So that's important to write stuff down. And then definitely sit in on other defenses that you can get an idea of how they go, what kind of questions the committee will ask, and then ask other grad students to give you feedback on chapters. Younger grad students, they're worrying about writing and everything. So by you letting them read your chapters and asking for feedback, it kind of gives them an idea of, what they need to do. So you're helping each other. And then do practice defense presentations and have your friends sit in, ask questions. It takes a couple hours to do all that kind of stuff, but I found it to be very, very helpful. So after my time at Auburn, I wanted to still do plasma physics, but I wanted to kind of venture out to different areas of plasma physics. And so a postdoc is a great way to get experience in, not just experimental space plasmas, but go do a little bit of fusion, go do a little bit of laser fusion, stuff like that. So I did a 3-year postdoc appointment at University of Wisconsin-Madison. And I was working on the Madison Symmetric Torus, MST. And so this is kind of like a cartoon drawing of what it looks like. It's a really cool experiment. It doesn't use magnets. And so this aluminum shell that surrounds it, they use that as like one giant magnet. And then you have the iron core here, which drives some of the plasma current. And then the plasma is inside in the pink. So this is a really cool experiment. It's been around since the 80s. A lot of the scientists that kind of were working on it from the beginning still are staff scientists working on it. So it's really cool because the knowledge that works on that experiment is amazing. This is what it looks like in real life. There's a lot of stuff on it. You can barely even see the aluminum shell. So there's a lot going on it. It was a cool experiment to work on. But I got to continue traveling as a postdoc. I got to go to a lot more conferences and present my results, again, all over the US, and I got to go to Scotland and China. I worked on not just one project. In grad school, I worked on basically one project, but at MST, I worked on 4. So my main project was working on energetic electron generation during magnetic reconnection events. So MST has, sawtooth-like features. And so they're basically magnetic reconnection events. And so we were using this fast X-ray detector to study energized electrons. And we found that they're not runaway electrons. So they're not moving parallel to the magnetic field. they start off perpendicular in a perpendicular motion to the magnetic field, and then they go out, fly out to the edge, and then go into a parallel motion. So that was my main project. I also worked on system upgrades and data processing improvements for the fast X-ray detector and the other X-ray slower X-ray detectors that we had. I also worked on some MST tokamak experiments where we worked on runaway electron suppression. And when you use MST as a tokamak, you do get runaway electrons. And so that kind of became important for experiments like ITER. And so we were studying how to suppress runaways. I also worked a little bit on a project where we studied the effects of magnetic perturbations on some 3D plasma structures on MST. So after I left MST, I got some experience in industry and now in the government. So I spent 3 years at TAE Technologies there in Southern California in Lake Forest. I was a diagnostic scientist. So when I got there, we actually had an empty high bay. Now they have C2W, which is this big giant machine. And so I actually got to watch them build it up, which was really cool. But while I was there, I designed and implemented a lot of different types of diagnostics. I did a bunch of types of Langmuir probes, I think 3 or 4 different bolometer systems, magnetic sensors. And so all of this was used to study edge temperature and density profiles. With the Langmuir probes, we had started studying electrostatic fluctuations, some fast ion losses, and then with the magnetic sensors, we studied the effect of eddy currents due to these fast switching coils that we had in the inner diverters here. So after 3 years at TAE Technologies, some of the guys at the Naval Research Lab that I'd worked with in grad school called me up and said that they had a position open. And you know, if I wanted to come work with them to come on to Virginia, to DC. So last summer, I started working there. So this is the space chamber. It's two separate parts. We have the smaller source chamber and then the bigger space chamber. I've been mostly working in this machine, this part of the machine since I started there. So I'm a research physicist and I'm studying experimental space plasmas. And so this is important because it can be really hard to study satellite data. You know, the satellites have to be at the right place at the right time. And sometimes that's not always possible. Sometimes you only get one data set and maybe you are never in the right place at the right time again. So we can take these phenomena that are seen in space and recreate them here in the space chamber in the laboratory, and we can do experiments to gain a more in-depth understanding of what's happening. And then we can take what we've learned and go and tell all of the space scientists, you know, here's the overall picture of what's happening in space. And, you know, the theorists will kind of bridge that gap between what we've learned in the experiment and what's going on in space. And so you really have these 3 different areas that are all working together to get this better understanding of what is going on and, you know, how it affects space weather. You know, satellites can be vulnerable to GPS satellites, vulnerable to space weather. So if you understand more about what's happening, it makes it a lot easier to maybe learn how to prevent things from breaking. So right now, I'm working on a diagnostic, developing a diagnostic for more accurate measurements from sounding rockets. And we actually have one of these diagnostics on the International Space Station. So what I've been learning in the lab I've been, you know, discussing with other people in our group who are working on the ISS data to help kind of interpret the data from that diagnostic. So it's been really cool, you know, going back to studying space plasmas in the lab. After all that, you know, what does it really take to become a physicist? I didn't really know what being a physicist meant when I decided to become one. You know, a lot of people now, they find out I'm a physicist and they're like, oh, it's like Sheldon or, you know, Big Bang Theory. And people think that you have to be like a super genius to become a physicist. And I don't think that's true. I think you have to work really hard at it. I would not say I'm a genius by any means. I'm just really hardworking. So it takes a lot of hard work, a lot of patience, persistence, resiliency, and it takes just a little bit of good luck. You know, when you're running your experiments, things don't go well a lot of the time. So sometimes you just need that one day when all the physics gods are, you know, looking down on you, and you get a good day of data taking, and sometimes that's all it takes. So now that I'm an experimental plasma physicist, I really enjoy performing experiments in the lab, especially to help understand what's going on in space. It's really fun to, you know, take this satellite data and turn that in, you know, with your hands, building stuff, installing stuff, making stuff work, turning, you know, this laboratory experiment into space, basically. The work is never boring. Every day is different, and I'm constantly learning new things. And as I said before, you know, it's experimental work, so it is hands-on. You know, you're using tools and you're in the machine shop, and you're writing your own codes, and so you're kind of all over the place doing everything. And I still love the aspect of getting to travel for conferences. It's been a really good way to be able to see the world by traveling. And so, you know, I wanted to be a physicist for NASA. Obviously, I'm not. I did get to work at NASA as an intern, but there's a lot of other options. You know, you can go into academia, you can do research-based industry like TA Technologies does. I have a friend who studied dusty plasmas, and now he works in manufacturing-based industry. He works at Intel. You can also do government or national labs. So there's a lot of different options. Sometimes you just have to kind of look for them. And then looking back, advice that I might give to high school Amy, I stressed out a lot in the later part of college and grad school. Pulled a lot of all-nighters. I would not recommend that. Don't stress out, like just work hard. Don't stress out. Everything will come together, and definitely do not pull all-nighters. I had an experience in grad school. I pulled an all-nighter, and around 5 a.m. I was, you know, done with my assignment. And I was, all right, I'll go home, you know, change clothes, maybe eat some breakfast, come back to campus, and go to class, and I'll turn in my assignment. Well, I went home and I fell asleep, and I was an hour and a half late for class, so class was already over. And walked into my professor's office, and I told him what happened, and he was like, do not pull an all-nighter. It's just not worth it. Also, you know, in high school, I wanted to be a marine biologist. So my career path has deviated a lot from being a marine biologist. It's changed several times in the last 17 years. So it's okay for that to change. You don't have to have a plan when you leave high school or leave undergrad, and you don't have to stick to it. There's multiple paths for everybody. There's not just one part of physics that is fun. So, you know, don't be afraid to kind of look at other things other than, you know, focus in on your plan. And then the last thing that I would say to high school Amy is, when my defense time came, my parents lived 4 hours away, so they came down to school on my defense day, and they wanted to sit in on the defense, but I was beyond nervous. I was crazy nervous, and I thought that them being there would just freak me out even more. At the end of the day, I don't think I could have been any more nervous, so them being there wouldn't have really made me more nervous. So I would tell high school Amy, if your parents want to be there, let your parents sit in on your defense. It's not going to hurt. They've been cheering you on for the last however many years that you've been in school. They've been there with you. So let them sit in. So I think that's it from me.
Thank you, Amy. So we're gonna open it up for questions. Go ahead and put it in the chat if you guys want to ask the questions yourselves. Just let us know. Let's go ahead and get started with the first one. Astrid, you wanna go ahead and go before Amy,
Sure, yeah, I can start off with some questions as people are thinking of stuff. So I had a question. You've kind of answered a lot of the questions already that I had, but what skill do you think helped you the most as a plasma physicist that kind of like translated throughout your career?
Like what skill or what class?
Really just anything, like a tool, like programming, skill, class, just kind of that you seen kind of carry throughout your career as a plasma physicist.
I think really just my interest in space, really, because everybody thinks of space as being a vacuum, but the more I got into plasma physics, the more I was like, it's not a vacuum. There's all kinds of stuff going on in there. So I think that really just helped me keep going when things got hard. Definitely my will to learn, especially I had never been out in the garage like working on the car, so going into the machine shop was new for me, but I think that will to learn new things and be willing to go and learn new tools and go down to the machine shop and just not be afraid to make mistakes. I think that probably helped me the most.
Thank you. So we have another question, I guess an anonymous question. What types of clubs, research opportunities, or internships do you suggest for us to participate in? Do you suggest we stick with the same club or research for a longer period of time or try different ones?
I think it depends. If you're not really sure like what you want to do, then definitely try different research groups, research projects. If you absolutely know that you want to do this very specific type of plasma research, then yeah, do a longer term project. I think it looks great if like an undergrad or younger student sticks with a project that they're passionate about, and maybe they do a couple presentations at a conference, or maybe they're co-author or first author of a paper. I think that looks great. So as far as opportunities, the opportunities that I came across, just they kind of fell into my lap. I didn't really go searching for them. So I know the Naval Research Lab, they do like a high school like kind of intern program. And so that's the one that I can think of off the top of my head. Other than that, if you talk to other grad students or professors, they can probably point you toward other ways to find opportunities.
Great, thank you. Okay, so we have another question. What is your opinion on the importance of persistence in research?
That's a good question. So you definitely need to be persistent. Every time something gets hard, you shouldn't go, running to somebody for help. You should try to work through the problem yourself. Something that I probably still struggle with to this day is knowing when the point comes that you should go and ask somebody for help. That's always been a problem, from when I was taking classes, doing my homework. The reason I pulled all-nighters is because I refused to go ask for help. I would sit in my office struggling for hours to get something done. So you definitely need to be persistent, but you need to be smart about it. If you're not making any headway, go ask for help. If you're being persistent, but you're not really having any fun in your research, then maybe it's time to go talk to somebody about other options.
Great. Do we have more questions? So how do you deal with being one of the few women in the field? Did you ever feel like it was an obstacle?
So in my high school physics class, I was also the only girl. And I remember being the only girl, but I don't really remember it being an obstacle. Even when I got to college, so our department at Florida Tech was the physics and space science. And so we had a lot of women in our department, but they were mostly in space science, which didn't seem to make a difference until later years in college when the core classes kind of got separated. So I never really felt like it was an obstacle until I kind of got to grad school. And it was more an obstacle because I felt like maybe I had to prove myself more to the guys than they had to prove to each other. Since I've gone past that, once I started doing my research, I was the only girl in the lab. Everybody was super nice and helpful. If I needed help, nobody even questioned, coming to help me or showing me how to use a new tool in the machine shop or anything. I haven't felt like it's been an obstacle because nobody's made it to be an obstacle. It's just been in the back of my mind, like I am the only girl, but it hasn't really affected how I've gone forth, I guess.
Okay, thank you. So another question, do you think a postdoc is important if you're going into industry research, like the Navy Research Lab?
So I know at NRL, they have a program where you can come in and be a postdoc. I forget what the program is, but that kind of it kind of turns into, a lot of the national labs are like this. You kind of go and do a postdoc at these labs for a temporary work assignment. And then if you do a good job and they like you, they'll hire you on permanently. So if you want to go into national lab or NRL government kind of route, I think it is important to do a postdoc, not necessarily with them, but if you can do a postdoc with them, it makes it easier to kind of get in. But it is helpful. If you want to go into academia, I think it's highly recommended to do a postdoc. If you want to go into industry, I really don't think that a postdoc is necessary. At Tri-Alpha, I was one of the few that did a postdoc. A lot of people did not.
Great. So I have another question. Do you have any tips on networking and how to kind of grow your network as you go through your career?
That's a good question. Conferences are a great way to network. You go to the poster sessions and just start, talking to people and asking questions. I've actually made a lot of friends through that. I have no other connections to people at these conferences other than we're there every year. And so you get to know each other and start following each other's research. Same thing goes with, professors. If you think their research is interesting, you can go and talk to them at posters. A lot of conferences will have, networking opportunities outside of like the official conference hours. They'll have little get-togethers and stuff. So I definitely recommend going to stuff like that. Your professors should be introducing you to other groups too. One of the things I found helpful was I was the only girl in my lab, and my advisor's good friend, his lab only had one girl. And so at conferences, us two girls used to room together. So we became friends. And through that, I became friends with all of the people in her lab group. And now I know her, who her advisor was, and all of their new grad students. And then, through that kind of family, you get to know, other people. So getting, networking with people through that your professor knows is really, really, really helpful.
Thank you. So unless anyone has any more questions, we have one more, and then we should probably wrap it up. But again, if you have last minute questions, you can put them in the chat now. But the last question I see is, do you think it's important what college you go to, or what grad school you go to?
No, I don't. I like to think that I kind of started at the bottom and worked my way up. Most people haven't ever heard of Florida Tech before. It is a small private school on the east coast of Florida. When most people think of Auburn University, they think of football. But Auburn has a good physics program. They have a really well-known plasma group, Ed Thomas's group. They do the dusty plasmas and still some space plasma experiments, and they also have a small fusion group there. But they're middle of the road. And then I went to do my postdoc at Wisconsin, which is a really well-known plasma group with lots and lots and lots of different experiments. I think everybody that works on those experiments is really well known. So I think it depends on what you make of your experiences. You should go to a school that has what you want, that makes you feel comfortable. If you don't want to go to a big school like Wisconsin had a huge student body. I don't think that you have to go a certain route. I don't think that you have to go to Princeton for undergrad and grad school to be successful. It's all of what you make of your opportunities.
Okay, we did get another question. How does one manage to handle both the experimental and theoretical aspects of physics projects? Do you think it's important to get enough experience in both fields?
So that's a good question. I think it is important to get a feel for both. If you want to be a theorist, some people are not meant to work in the lab. Some people, shouldn't be handling tools, and in early grad school that becomes obvious. Who shouldn't be in the lab and who should be. But I do think it's important because some theorists, they will come to an experimental group and ask them to do something, and sometimes it's impossible. So I feel like if you get both aspects, then you kind of understand what's possible to do in theory and what's possible, to bring theoretically into the lab and say, do this. So you do need to get a little exposure to both. I am by no means a good theorist. I was really lucky. All of my theory, I had a lot of help from a great theorist at NRL. And so he was willing to sit there with me and explain every little detail of all of these equations and how he got step to step. And so I would suggest that you find somebody to help you with that aspect if you're going to be an experimentalist.
Okay, so this will be our final question.
Okay.
So do you think we can accomplish fusion in our lifetime?
I hope so. There's a lot standing in the way of it still, and I don't even think it's a plasma physics problem. I think it's more of a problem with materials, like material science. So I would say if we get a lot of good people in material science and we can solve problems like that, then yeah, I think it's achievable in our lifetime. Um, it's certainly not going to be easy. So, you know, everybody who wants to go into fusion and material science certainly keep sticking with it. That's where the persistence comes in. Persistence is important with a problem like that because it's very hard. And you just have to keep working at it and find new and innovative avenues to go down. But I think it's possible if we can solve the problems that have come up right now.
Okay, well, thank you so much for your talk. We're all just virtually clapping, I'm sure, in our respective places.
All right, thank you guys. Thank you everybody who came out, and we really appreciate it. Most of you will be receiving, if you registered on Zoom, will be receiving an email from me and Astrid with more of the links to our websites and our social media pages. And if you'd like to hear more or get more information about our organizations at UCI, then we're more than welcome to add you guys to lists, email lists, and send you more information. All right. Thank you guys, and have a good night. Thank you, Dr. DuBois.
Thank you, Ernesto, and thanks for everybody for listening.